this is angular momentum. Angular momentum depends on mass, shape, and also the speed of rotation. It gives the idea that what amount of rotation a body has. It also gives the idea how far is the axis of rotation from the body. It might be taken as the product of radius vector and the linear momentum vector. See, in the figure it's very apparent. This is the axis of rotation. Axis of, hope this is visible to you clearly. Axis of rotation. This is the point of application here. Radius vector would be considered from the axis to the point. The direction of momentum vector is small p, it's here. Then angle between P and R is theta. This R sine theta equal to capital R. What is capital R? That is the perpendicular distance of the axis of rotation from momentum vector. If you just simplify in the form of vector product, you might say this is equal to PR sine theta, that is P into R. P into R, what is that? This is the product of perpendicular distance and momentum. We might say angular momentum is equal to the product of linear momentum and its perpendicular distance from the axis of rotation. Sometimes it is also called moment of momentum. That looks very rhythmic in just utterance. Moment of momentum, but second momentum stands for linear momentum. It could be written as mv into r, this as well. See, here P sine theta appears in the relation, not P cos theta. So you might say that this radial component doesn't contribute to angular momentum, only the tangential component is meaningful. You can also say if the point lies on the radial vector, then the angular momentum about it shall be equal to 0. You know this relation J equal to R cross P. If we differentiate this whole relation, we'll find R cross dp dt, then dr dt into P. See, this is dj dt. You might write delta j delta t. This is R cross nothing but force. You know, force is equal to rate of change in momentum. So this is equal to force. And here, this thing I write separately, V cross P. V and P both are linear. Obviously, their cross product shall be equal to 0. So V cross V, this whole thing vanishes over here. It's 0. And final result is this one. Delta J upon delta T, you know, this is called torque. You know, this relation, torque is equal to delta J upon delta T. So torque is equal to R cross F. Torque is equal to delta J upon delta T. This is also one relation between torque and angular momentum. This relation quite similar to force equal to dp dt. Regarding angular momentum, if you find the dimension from this relation, you'll find ml2 t minus 1. This will contribute to the dimension as kilogram meter square per second. But since this is something to do with rotation, angular velocity is there. Actual unit for this also is written as radian per second. This thing. This is the complete unit if we consider other relation for angular momentum. If we consider this relation, the unit we find is kilogram meter square per second. From dimensional point of view, both the units are same. Its dimension itself is very important. It has in fact the dimensional resemblance with that of Planck's constant. You know, Planck's constant is the backbone of modern physics. The whole quantum theory is based on this thing. And this resembles with angular momentum, so it becomes very important. It finds the application even in Kepler's second law also.